Let us move to the next law, that is Avogadro. This law relates the volume and amount of the gas. Hence, statement of this law is under similar conditions of temperature and pressure. Under similar conditions of temperature and pressure, equal volumes of gases, equal volumes of gases containing equal number of molecules. So whatever may be the gas, under similar conditions of temperature and pressure, equal volumes of gases contain equal number of molecules. So from this we can say that, or mathematically we can write it as volume is proportional to n, or V is equal to K into n, where K is a constant. K is a constant. So this is about the Avogadro law. Avogadro law relates the volume and amount under similar conditions of temperature and pressure. Equal volumes of gases contain equal number of moles. We know that 1 mole is nothing but 6.022 into 10 to the power 23 particles. If you take molecules, it may be molecules also. So this number is called as, represented as Na, which is called as Avogadro's constant. Avogadro constant. So we can say that 1 mole of any gas containing 6.022 into 10 to the power 23 molecules. This value is called as Avogadro's constant. At STP, STP is nothing but standard temperature and pressure. At STP, the temperature which is called as standard temperature, its value is 0 degrees Celsius or 273.15 Kelvin. Standard pressure, if you take, the value of standard pressure is 1 atmosphere, or it is also equal to 10 to the power 5 pascals. Okay, so this is the value of standard temperature and standard pressure. At STP, 1 mole of gas, 1 mole of ideal gas, right? What do you mean by ideal gas? Ideal gas is nothing but the gas which follows Boyle's law, Charles' law and Avogadro's law. Ideal gas occupies a volume of 22.71 liter per mole. Means 1 mole occupies this much liter, 22.7 liter per mole. Now we know that number of moles N is nothing but mass of gas divided by molecular mass. We can write it as Small m mass, capital M molecular mass. If you substitute n value in the mathematical form of Avogadro law, you can write V is equal to K into n, or K into n is m by m. Okay? Here V is proportional to n, or V is equal to K into n. V is equal to K into n. N is nothing but number of moles. Number of moles is nothing but mass by molecular mass. We can also write it as capital M, that is nothing but molar mass. Molar mass is equal to K into, I bring this V to the denominator of right hand side. So M by V. M by V is nothing but density. Okay, so we can write it as K into D. So M is equal to K into D. From this we can say that M is proportional to D. That is nothing but molar mass. If you remove the constant, you get proportional to simply. So M is proportional to D means molar mass is directly proportional to density. Molar mass is directly proportional to density. Okay, so this about the Avogadro's law, which relates volume and amount relationship. Amount of gas, if we take n number of moles we can say. So under similar conditions of temperature and pressure, equal volumes of gases contain equal number of molecules. Here I have taken n as number of moles, then I converted moles into molecules. So V is proportional to n. V is equal to K into n, where K is a constant. We know that 1 mole is nothing but Avogadro number of molecules. At STP, that is standard temperature 0 degrees Celsius, it is nothing but 273.15 Kelvin. Standard pressure 1 atmosphere or 10 to the power 5 Pascal. At STP, 1 mole of gas, means ideal gas, occupies a volume of 22.7 liter per mole. If you see these values, this 273.15, which is freezing point of water, and 1 atmosphere, it's the atmospheric pressure at sea level. So standard temperature pressure, these values correspond to temperature, correspond to freezing point of water, pressure correspond to atmosphere at sea level, atmospheric pressure at sea level. Next, let us move to the next concept, that is ideal gas. What is ideal gas? Ideal gas is a gas which follows Boyle's law, Charles' law and Avogadro's law strictly. It is called as an ideal gas. Okay, very important one. Ideal gas is one which is a gas which follows Boyle's law, Charles' law and Avogadro law strictly, is called ideal gas. Let us write the mathematical form of these laws. We know that according to Boyle's law states that at constant temperature, volume is inversely proportional to pressure at constant temperature. According to Charles' law, volume is proportional to temperature. Condition is what? At a constant pressure. Avogadro's states that under similar conditions of temperature pressure, equal volumes of gases contain equal number of moles, but condition is under similar conditions of temperature and pressure. So these are the mathematical form of three laws. Now let us combine all these three. Left hand side B, left hand side B, left hand side B. Denominator P, numerator T, numerator N. So I can write it as V is proportional to N into T divided by P. Or I'll bring P to the left hand side. P into V is proportional to N into T. Now we have to remove this proportionality symbol. To remove this proportionality symbol, we have to use a constant. So PV is equal to, I use a constant R, N, R, T, where R is a constant called universal gas constant. Universal gas. What about its unit? Its unit depends on, if you write R as R is equal to PV divided by N T. R is equal to PV divided by N T. The unit of R depends on units of pressure, volume and temperature. N anyhow number of moles. Okay. Let's find out the value of R. Value of R. There are many units to measure R. If we take one method only, in the first method, if we take pressure in pascals and volume in meter cube, then we can write at STP, we can also write this as R is nothing but P into V divided by N into T. P is nothing but 10 to the power 5 Pascal, which is also equal to 1 atmosphere. Value of V for 1 mole is at STP 22.71 into 10 to the power minus 3 meter cube divided by N. Let us take it for 1 mole. Temperature, we know that 273.15 Kelvin. If you simplify this one, 10 to the power 5 into 22.71 into 10 to the power minus 3 divided by 1 into 273.15. On simplification, we will get 8.314 Pascal here meter cube, here per mole, this one per Kelvin. Again on simplification, Pascal meter cube can also be simplified as 8.314 into 10 to the power minus 3 bar liter per Kelvin per mole, or 10 to the power minus 2 bar liter is nothing but joule. So 8.314 joule per Kelvin per mole. Volume is 22.71 liters. Number of moles is 1 mole. Temperature is 273.15 Kelvin. On simplification of this, we get 0.0831 liter atmosphere per Kelvin per minute. So we can also use this one. Okay. One is 8.314 joule per Kelvin per mole. Another unit of universal gas constant R is 0.0831 liter atmosphere per Kelvin per mole. So these are the two units to measure R. We know that ideal gas which follows Boyle's law, Charles law and Avogadro's law strictly. So the equation we got combining these is PV is equal to nRT. This equation is called as ideal gas equation. This is called as ideal gas equation. If you write this one as PV divided by T as nR, then we can say that in two different states, pressure P1, volume V1 and temperature T1 changes to pressure P2, volume V2, temperature T2. Once again, in one state, pressure is P1, volume is V1, temperature is T1. That state is changed in such a way that pressure becomes P2, volume becomes V2 and temperature becomes T2. Now using ideal gas equation, we can write P1 V1 by T1 is equal to P2 V2 by T. But because they are constant, n number of moles constant. If it change from one state to another state, number of moles constant. R is anyhow constant, it is a universal gas constant. So since this is constant, we can write P1 V1 by T1 is equal to P2 V2 by T2. This number of moles constant when changes from one state to another state, then only it is constant. Universal gas constant R is anyhow constant. Okay. So we can use P1 V1 by T1 is equal to P2 V2 by T2. This is called as this is called as combined gas equation. This is also called as equation of the state because any gas in this condition represents the state of the system and so it is called as equation of the state. Equation of the state. Let us take how the density and these combined gas equation are related. In the case of combined gas equation, how density is related. Okay. So next one is density and molar mass of a gaseous state. We know that PV is equal to nRT, which is ideal gas equation. N is nothing but mass by molecular mass, which is number of moles. I will bring this N to the RT. M by capital M, it goes to numerator, so P by RT. That's it. M by V is nothing but density. Density by molar mass is equal to P by RT, or density is equal to Pm by RT. Density is equal to Pm by RT, or we can write molecular mass as M is equal to density into universal gas constant into temperature divided by pressure. Okay, once again we know that PV is equal to nRT, which is a ideal gas equation. N by N by V is equal to P by R. N is nothing but number of moles. Number of moles. N is equal to mass by molecular mass. So mass by molecular mass divided by volume is equal to P by RT, or M by small m by molar mass into volume is equal to P by RT, or M by V. This M by V is nothing but density. Density by molar mass is equal to P by RT, or density is equal to C into M divided by RT. You have to use small p. Okay, or M is equal to dRT by T. Okay, so this is the relationship between molar mass and density. Now tell me how they are related. Molar mass and density. Here R is constant. So relation between them is like this. Density is equal to pressure into molar mass divided by universal gas constant into temperature, or molar mass is equal to density into R into T divided by T. Let's solve some problems related to combined gas equation. We know that combined gas equation is P1 V1 by T1 is equal to P2 V2 by T2. Okay. Here one problem. A sample of gas occupies a volume of 2.74 dm3. 2.74 dm3 at 0.9 bar and 27 degrees Celsius. So this is volume, this is pressure, this is temperature. What will be the volume at 0.75 bar means pressure and 15 degrees Celsius temperature? So we have to find out volume. So from the given data, okay, initial volume V1 how much? 2.74 dm3. Pressure P1 0.9 bar. Temperature T1 27 degrees Celsius. We have to convert it into Kelvin is equal to 300.15 Kelvin. Next it changes into what will be the volume at 0.75 bar. So P2 is equal to 0.75 bar. Okay. Temperature is 15 degrees Celsius is equal to 285.15 Kelvin. What you have to calculate? We have to calculate V2. V2 is equal to how much? We know that P1 V1 by T1 is equal to P2 V2 by T2. Let's substitute, then find out V2. So V2 is equal to P1 V1 by T1 into T2 divided by P2. On substitution, we will get P1 0.9 into V1 2.74 into T2 285.15 divided by T1 300.15 into P2 0.75. Okay. On simplification, we will get 3.156 unit of volume here dm3. So V2 also dm3. Okay. Once again, in the initial state, these are the variables. Which are the variables? Volume, pressure, temperature. It is changed into next state. Their variables only pressure and temperatures are given, but volume is not given. Our intention is to calculate volume. We know that combined gas equation is given as P1 V1 by D1 is equal to P2 V2 by D2. So V2 is equal to P1 V1 by D1 into T2 by P2. On substitution, 0.98 into 2.74, 285.15 divided by 300.15 into 0.75. On simplification, we will get 3.156 decimeter cube. It is the volume at stage 2. Similarly, let's solve one more problem. A sample of nitrogen gas occupies a volume of 1 dm at a pressure of 0.5 bar and 40 degrees Celsius. Calculate the pressure of the gas if compressed to 0.225 dm at minus degree Celsius. So here also first let us write from the V1 delta. In initial state, volume is given. How much? 1.0 means 1 decimeter cube means liter. Pressure P1, how much? 0.5 bar. Temperature is 40 degrees Celsius. We have to convert this into Kelvin. So we get 330.5 Kelvin. Okay. Calculate the pressure is asked. So we have to find out P2. If the gas is compressed to 0.225 dm cube, so V2 is equal to 0.225 dm cube at minus 6 degrees Celsius. So T2 is equal to minus 6 plus 273.15 is equal to 267.15 Kelvin. What is combined gas equation? P1 V1 divided by T1 is equal to P2 V2 by T2. Our intention is to calculate what? Pressure P2. So P2 is equal to P1 V1 by T1 into T2 by V2. On substituting, we get P1 0.5 bar, V1 1 dm cube, T2 267.15 divided by T1 313.15 Kelvin into V2 0.225. On simplification, we get 1.895 unit of P2. P1 is bar, so P2 also bar. this is the unit of P. Value of P2 is 1.895 bar. Once again, this problem is similar to earlier one. Here also, in the initial state, volume, pressure, temperatures are given. In the next state, only volume and temperatures are given. Pressure we have to find out. So we know that combined acid equations is that P1 V1 by V1 is equal to P2 V2 by T2, or P2 is equal to P1 V1 by T1 into T2 by V2. On substituting the value, we get P2 as 1.895 bar. In the next concept, we are going to study the fifth law, that is Dangans law of partial pressure. Dangans law of partial pressure is related to pressure of the non-reacting gases. If a mixture of non-reacting gases are taken in a vessel, how does their total pressure varies? That is given by Dalton's law. The statement of law is like this: the total pressure of the mixture of non-reacting gases is the sum of the partial pressure of the individual gases, that is pressure exerted by these gases if they were enclosed in a same volume vessel under similar temperature. Okay, so we can write it as the total pressure of a mixture of non-reacting gases is the sum of partial pressures of individual gases. That is, if they are present in a container having same volume and same conditions of temperature. Okay. Mixture of non-reacting gases. And then, for example, A is the one gas, B is the another gas, C is the another gas. If they are mixed together, ಅದು react ಆಗಬಾರದು. A, B, C ಯಾವುದೇ ಒಂದಕ್ಕೊಂದು react ಆಗಬಾರದು. That is called as non-reacting gases. Okay. If P total is the total pressure of mixture of gases, and P1, P2, P3 are the partial pressures of individual gases. Then P total is equal to P1, P2 plus P3. ಅಂದ್ರೆ 3 gases ತಗೊಂಡ್ರೆ 1, 2, 3 and 3 gases ಇದೆ. Total pressure of the mixture of gases is equal to sum of the individual partial pressures. P1 is the partial pressure of gas 1. P2 is the partial pressure of gas 2. P3 is the partial pressure of gas 3. So P total is equal to P1 plus P2 plus P3. What do you mean by partial pressure? Partial pressure means it is the pressure exerted by. It is the pressure exerted by gases are collected over water because gases are ನಮಗೆ ಯಾವುದೇ ಒಂದು ಕಂಟೈನರ್ ಅಲ್ಲಿ ಕಲೆಕ್ಟ್ ಮಾಡಲಿಕ್ಕೆ ತುಂಬಾ ಕಷ್ಟ. So we are collecting them in what above the water. ಈಗ for example ಒಂದು beaker ಈ ತರ ಇದೆ. Okay, if any gas is released by doing some reaction, if any gas is released, it is collected over water. If this is water, it is collected over water. Okay, so whatever the pressure present is total pressure. It is not only due to the gas released from here, it is due to the vapor pressure of this water also. Okay, the total pressure whatever collected here is not only due to the gas liberated here, but it also from the vapor pressure of this water. So we can say that generally gases are collected over water. Okay, so what about the pressure of the gas released? How to find out? So pressure of the gas is equal to total pressure, means pressure of the dry gas, right? Pressure of the dry gas is equal to total pressure minus vapor pressure of water. Due to the vapor pressure of water, some vapors are present, that gas also collected here. So you have to deduct the vapor pressure of water from the total pressure. Pressure of the dry gas is nothing but total pressure minus vapor pressure of the water. Whatever the pressure due to this water is present, that is called as aqueous tension. That is called as aqueous tension. What do you mean by aqueous tension? Aqueous tension is the pressure due to the water vapor. Pressure due to the water vapor. Next concept is partial pressure in terms of mole fraction. Suppose three gases, if you take, suppose three gases at temperature T and volume V, their partial pressures can be expressed as, okay, partial pressure of gas 1 is equal to nRT by V. Here I take n as n1 because partial pressure of gas 1 P1, it contains n1 number of moles, so I take n1. R is constant. For all these gases, temperature, volume are constant. Similarly, partial pressure of gas 2 is equal to N2 RT by V. Similarly, partial pressure of third gas is equal to N3 RT by V. If you write the total pressure, expression for total pressure according to Dangans law is P total is equal to partial pressure of the non-reactive gases. Means here three gases are there. So partial pressure of 1 plus partial pressure of 2 plus partial pressure of 3. Like that you can continue. Okay. Now, partial pressure of 1 is nothing but N1 RT by V. Partial pressure of 2, N2 RT by V. Partial pressure of 3 is N3 RT by V. Okay. By adding all these, P1 N1 RT by V plus N2 RT by V plus N3 RT by V. I take RT by V as a common factor, so remaining thing is N1 plus N2 plus N3 into RT by V. So this is the expression for total pressure. Now, dividing P total by partial pressure of 1. Okay, so P1 by P total is equal to P1 is nothing but N1 RT by V divided by total pressure N1 plus N2 plus N3 into RT by V. Here V and V get cancelled, RT gets cancelled. What is left? N1 divided by N1 plus N2 plus N3. So P1 by P total is equal to N1 by N1 plus N2 plus N3. What is this right hand side term? This is nothing but mole fraction of component 1. Under the first chapter, we have studied that mole fraction is represented by symbol X. X1 is equal to number of moles of that component divided by total number of components, like it continues. So X1 is equal to N1 divided by N1 plus N2 plus N3. Similarly, X2 is equal to N2 divided by N1 plus N2 plus N3. Similarly, X3 is equal to N3 divided by N1 plus N2 plus N3. So substituting this here, we get P1 by P total is equal to mole fraction of first gas, or partial pressure of first gas is equal to its mole fraction into total pressure. So like this, we can relate partial pressure and mole fraction in this using this relation. This is for gas 1. If you write it for gas 2, P2 is equal to X2 into P total. Similarly, we can write P3 is equal to X3 into P total. So these are the relations between partial pressure of individual gas and total pressure and mole fraction. Okay. So under this chapter, states of matter, we have studied about introductions to states of matter, characteristics of gases, different laws like Boyle's law, Charles' law, Gay-Lussac's law, Avogadro law, Dalton's law of partial pressure, etc.